Acidity of alcohols. Before moving on to the topic, let us take up a short story of a fisherman and his pet. The fisherman used to feed his pet with fishes that he had caught. One fine day, another fisherman came to the site and started fishing. The pet noticed that he could get fishes from this new fisherman pretty easily. So it grew fond of the new fisherman, and its affection towards its old master reduced. Now imagine the pet to be our oxygen atom, and the original fisherman as the hydrogen atom. The oxygen and the hydrogen share an electron pair, and this electron pair moves towards the oxygen as it is more electronegative. Now imagine the new fisherman to be an alkyl group, which is electron-donating in nature. The oxygen atom can easily get electrons from the alkyl group than from the hydrogen. This is analogous to the situation where the pet could get fishes easily from the new fisherman. Hence, the attraction towards oxygen of the shared electron pair is less than that compared to before. This reduces the polarity of the OH bond. The polarity of the bond was responsible for easy release of H+ or proton from the alcohol. Therefore, it can be said that the alkyl group reduces the proton-releasing ability of alcohols. In other words, it reduces the acidity. When the alkyl group contains a secondary or a tertiary carbon, the electron-donating capacities would increase further, and this would further reduce the acidity. Hence, the primary alcohols have a greater acidity than secondary and tertiary alcohols. Now, let us compare the acidity of alcohols and water. In the reaction between an alkoxide and water, it is water that donates a proton. Hence, it is a better proton donor than an alcohol. Also, we see that the alkoxide ion accepts the proton and not the hydroxide ion. Hence, alkoxides are stronger bases than hydroxides. So these alcohols also act as Bronsted-Lowry bases due to unshared pair of electrons on oxygen.